Euro 412 UTC on October 21st, 2025, NASA's Deep Space Network recorded its final confirmed telemetry packet from the interstellar object known as 3I Atlas. Within the hour, the signal dropped below threshold detection. The loss was expected, and yet it arrived with a weight that no one inside the network could fully articulate. Atlas had entered solar conjunction, crossing the line of sight between Earth and the Sun. For the next 21 days, the world's most advanced optical and radio observatories would be blind. The event marked a rare intersection of coincidence and consequence. The third confirmed interstellar object ever detected, Atlas was first cataloged in July 2025 by the Atlas Survey in Chile, its hyperbolic velocity confirming an origin beyond the solar system. Since then, every major observatory, from the James Webb Space Telescope to the European Space Agency's Solar Orbiter, had been tasked with collecting data. Its trajectory, nearly aligned with the plane of the planets, and its composition, rich in carbon dioxide but poor in water, defied established models. Even so, up until the final hours before conjunction, Atlas's motion obeyed gravitational predictions within measurable limits. The purpose of continued observation was simple. Verification. Scientists sought to confirm whether its course would remain consistent as it passed perihelion, the closest point to the Sun, where thermal stress, radiation pressure, and outgassing typically drive natural comets into chaotic dispersion. The last data sets from SOHO and STEREO showed nothing unusual in brightness or motion. Instruments reported stable magnitude, steady polarization, and a predictable deceleration curve as solar proximity increased. Everything appeared nominal. Then, without transition, the light signature intensified. At 0409 UTC, 3 minutes before contact was lost, coronagraph sensors recorded a luminosity increase by a factor of 3.7. Simultaneously, the spectral profile shifted towards shorter wavelengths, indicating a source temperature exceeding that of the solar photosphere itself. This single frame contradicted all known models of cometary behavior. If the readings are accurate, Atlas was radiating energy hotter than the Sun while moving deeper into its gravitational well. Telemetry ended before confirmation could be made. The object passed behind the solar disk, leaving the network in silence. What remains now is a gap, a blind window where every prediction collapses into uncertainty. And somewhere within that silence, Atlas continues to move. The anomaly first appeared not as a failure, but as a discrepancy, a single inconsistency in a series of otherwise precise measurements. When cross-referenced across observatories, the timestamp matched exactly. EO4809 UTC. The sudden brightness increase from 3I Atlas was not gradual, not the product of sublimation or surface fracture. It manifested as an instantaneous surge, recorded simultaneously by 3 instruments operating at different vantage points: the SOHO LASCO C3 coronagraph, the GOES 19 CCR1, and ESA's Stereo A HI1. Each registered the same impossible metric, an emission temperature exceeding 6,000 Kelvin, hotter than the photosphere of the Sun itself. Under normal conditions, comets approaching perihelion follow well-understood thermodynamic laws. Volatile ices sublimate as solar radiation intensifies, driving jets of vapor that increase luminosity logarithmically, typically following an R4 or R5 curve relative to distance. Atlas broke from that pattern entirely. The recorded rise in brightness followed a factor closer to R7.5, a slope consistent not with natural reflection or gas emission, but with an internal release of energy. Even more unsettling was the spectral shift. Blueward, when physics predicts red, dust scattering under intense radiation should redden a comet's reflected light. Instead, Atlas's spectrum migrated towards shorter wavelengths, indicating a higher effective temperature or an unknown mechanism of emission. Several hypotheses were proposed within hours of the blackout. The first, conservative and statistically grounded, attributed the anomaly to instrument saturation, a calibration artifact caused by solar background noise overwhelming the detectors. yet independent cross-calibration between instruments dismissed this. The readings were consistent across multiple optical systems with different sensitivity thresholds. A second theory posited that Atlas's nucleus might contain highly volatile compounds, perhaps metallic cyanides or carbonyls, undergoing exothermic decomposition under extreme heat. This could, in principle, generate transient bursts of luminosity. The flaw lies in magnitude. No known chemical reaction could sustain that energy output over seconds, much less across the 300,000 kilometer halo detected by CCR1. A third explanation ventured beyond chemistry into plasma dynamics. Some researchers suggested that magnetic reconnection within the coma, a temporary coupling between the object's magnetic field and the solar wind, might have created a short-lived radiative event. However, magnetohydrodynamic modeling found the required field strength unrealistic for an inert body of Atlas's mass and composition. The energy budget simply does not balance. Each interpretation remains incomplete, overlapping only in what they fail to explain. The surge was real, the data align, but its origin defies replication and simulation alike. For now, the scientific community stands suspended between three inadequate models: instrumental, chemical, and magnetic, while the object itself remains beyond observation. Only when Atlas reemerges from behind the sun will the next sequence of measurements determine which theory, if any, survives contact with reality. For mission control, time is no longer abstract. It has become a measurement of light, delay, and silence. From Earth's perspective, the event unfolds in layers, not continuous, but staggered by distance. Every signal from the inner solar system takes just over 8 minutes to arrive, traveling at the finite speed of light. The moment Atlas disappeared behind the sun, that delay transformed into absence. Now, the network counts not by seconds, but by orbits, waiting for geometry to shift, for the line between the object and the star to open again. The first phase has already closed. Observations ceased as solar elongation fell below the safe threshold for optical instruments. The Parker Solar Probe and ESA's Solar Orbiter, the only spacecraft with partial visibility, are now beyond their telemetry windows, their antennas oriented for thermal protection. From this point until mid-November, no direct data can be collected. It is a total blackout, a necessary one, imposed by physics and protocol alike. What occurs in that interval will not be recorded in real time. Only its consequences will be measurable afterward. In mission logs, the timeline reads as a sequence of diminishing certainties. October 21st, final signal lock. October 29th, predicted perihelion. November 7th, minimal safe solar elongation for reacquisition attempts. Each entry marks a narrowing of human reach. The instruments are ready, automated, but the sky itself will not permit a view. All that remains are the parameters of anticipation. If Atlas underwent natural fragmentation, the brightness will spike again upon reappearance. If it performed a gravitational maneuver, its trajectory will deviate from projection by measurable arc seconds. Either outcome is visible only when the sun releases its hold. Across observatories, countdown clocks run in quiet synchronization. In Chile, the Atacama mirrors are stowed, waiting for dawn geometry to shift. In Pasadena, data analysts model orbital variance scenarios hour by hour, plotting potential reentry vectors into the night sky. In Darmstadt, ESA's control room maintains passive tracking through radio silence, listening to nothing, logging everything. The entire network orbits around absence, the expectation that something will emerge. When visibility returns, the first photons of reflected light will travel 200 million kilometers before touching Earth's sensors. They will define whether Atlas remains a fading comet or becomes an entry in another category altogether. Each passing minute draws the line closer. The countdown continues, not toward an event, but toward an answer that could alter what the word trajectory truly means. In the days following the blackout, the public record changed tone. What had been a constant stream of coordinated updates narrowed to silence. NASA's official channels, once publishing hourly perihelion briefings, transitioned to a single daily statement: no new data at this time. The European Space Agency mirrored the restraint, releasing only geometry confirmations and general orbital estimates. Independent observatories requested access to the most recent telemetry frames, but were referred to non-disclosure protocols activated during conjunction. The data was not lost. It was classified for verification. Internally, the situation was less orderly. Analysts at multiple research centers reported inconsistencies in archived datasets: small, precise, and irreconcilable. Photon counts from the final minutes before loss of signal differed slightly between instruments that had been cross-calibrated to within 0.1%. The discrepancy was only a few units in intensity, yet it persisted through every correction. What appeared trivial on paper carried weight. It implied that at the exact moment of observational cutoff, the source itself may have changed in nature or in structure. Scientific interpretation fractured along institutional lines. Planetary scientists argued for natural instability, the possibility that Atlas's surface layer vaporized under peak irradiation, producing a temporary superheated sheath. Plasma physicists, by contrast, viewed the readings as indicative of electromagnetic induction, a response to intense solar interaction rather than a loss of material. A smaller group within orbital mechanics proposed a subtler, disquieting option: that the variation reflected not intrinsic change but spatial displacement. If correct, Atlas had altered its path in a manner not accounted for by any gravitational model. Each explanation demanded patience. None could be confirmed until the object re-emerged from behind the sun. Still, the pressure of silence grew. When independent researchers attempted to reconstruct the missing segment using heliospheric models, their results were withheld from publication pending data integrity review. By the second week of November, the blackout had become procedural, a coordinated pause that reflected more than caution. It signified control. Then, at 0318 UTC on November 11th, the Solar Terrestrial Relations Observatory registered a faint optical anomaly near the predicted exit coordinate. The signal was brief, lasting less than 2 minutes. Brightness matched Atlas's expected magnitude. Position did not. For several hours, no additional data appeared. Transmission logs show no errors, no confirmations. Only the final annotation entered manually by the tracking operator. Object reacquired. Offset exceeds model prediction. The record ends there. The recovery of 3I Atlas from solar conjunction marked neither triumph nor failure, only a return to observation. The object reappeared where no calculation had placed it, its trajectory displaced by a fraction of a degree that mathematics insists should not exist. That deviation, though small, translates to tens of thousands of kilometers across the span of interplanetary space. It is measurable, undeniable, and without precedent. Every subsequent analysis begins from that single fact. Something changed during the blackout. What followed was a global recalibration of both instruments and expectations. Tracking arrays were synchronized again, orbital models rewritten line by line, and yet the correction could not reconcile the anomaly. Atlas's new course implied an external force, or an internal one, that acted counter to solar gravity. The energy required was minimal by cosmic standards, yet vast by any mechanical frame of reference, an adjustment invisible in progress, visible only in result. No burst, no tail, no debris, just displacement. The consensus now divides between physics and philosophy. One interpretation holds that Atlas underwent a spontaneous structural event, an asymmetric release of material that altered momentum without fragmentation. Another suggests we have encountered a class of interstellar object whose internal composition, perhaps metallic, perhaps hollow, interacts with solar radiation in a way our models cannot yet represent. Neither explanation accounts for the precision of the movement or the sustained stability of its brightness since reemergence. What remains consistent is the data itself, clean, verified, and silent on motive. For science, the implications are procedural before they are existential. Every detection protocol built for passive observation must now anticipate the possibility of dynamic behavior in interstellar bodies. The next missions will operate not only as watchers, but as responders, capable of tracking what does not behave as predicted. The lesson is not that we have found intention, but that we have found limits in our equations, in our assumptions, in the reach of our instruments across the glare of a star. As of now, 3I Atlas continues outward, following a curve that no longer aligns with the models written before it vanished. Its brightness holds, its silence endures, and its deviation persists as a quiet constant in the night sky. In the end, all that can be said with certainty is that it came from beyond, passed through the measure of our understanding, and left the measure changed. The observation continues,